Well, the recorder is on, so I'm going to get started. We are finishing up predicate logic for the time being today. Okay, so I'm going to spend about 10 more minutes on it, and then we'll call it done. We will skip some of the stuff about proofs because I think we have been talking about proofs and predicate logic for a long time. So I'm going to interleave stuff in between a little bit. So we'll jump to discrete probabilities, and then we'll go back to proofs, a little bit later. Okay, because I just felt kind of, we have been talking about proofs, all along. Maybe we need to kind of rotate material a little bit here. So in terms of predicate logic, last time we used a prologue to do certain things, and I was trying to figure out, who is not a Jedi, and it could not answer the question. And the answer was actually pretty easy, because as soon as they can find, something that is not a Jedi, or something that is a Jedi, the negation of that is false already, and that's why it just says, okay, it's false. Okay, it does not go through the list and find out who meets the requirement of not being a Jedi. Instead, it finds a Jedi, negate it, and go like, okay, this is not a Jedi. I'm done. Okay, so that's why that did not work. It has to do with the resolution logic of the prologue. I spent a little bit more time on unification, so it is at the end of this note here. Okay, so I actually put in a little bit more notes regarding substitution and also unification, and a little bit on most general unification. So these are the new stuff that I put in. They're fairly abstract, because they have to do with the internal operation of prologue and how you can look at two well-formed formulae in predicate logic or first-order logic. It's basically the same thing, and say, can I look at these two as the same thing? Okay, can I unify? Can I combine these two into a single one? So these are the new concepts that I put in, but I'm not really kind of talk about these for now. Okay, so instead, what we'll do is to talk about something new, and hopefully something that some of you will be interested in. Okay, predicate logic is interesting. It has applications, but for the most part, people look at it and go like, well, that's kind of abstract and not particularly applicable on a daily basis. So I'm skipping proof techniques. There are notes that I have typed up already with proof techniques and also more proof techniques. Induction is something that's extremely useful, but once again, it's a proof technique, so we'll skip all of that stuff and we'll jump all the way to discrete probability for now. And then we'll go back and talk about the other ones, the topics that I have missed or intentionally have skipped over, at least for the time being. What? Okay, yep, go ahead. From the last lecture, so that would be from 2 days ago on the 17th. So it's not uploaded yet. Let's see. Okay, let's look up my channel. Sometimes I might have uploaded and it's locked. Oh, there we go. I forgot to press the unlock button. Let's see. How do I unlock it?
You set it to not private. You have it set to private right now.
Yeah, how do I change this setting?
You have to go to the video manager.
Yeah, that's what I thought. Publish. There we go. Okay, you can check whether it is now accessible. Your phone can probably get that too. All right, but thanks for letting me know. And getting back to here. So what we'll do is we'll kind of skip a little bit to talk about discrete probability, which is a kind of clean and nice break from all that logic stuff that we have been talking about, because this is kind of the opposite of things, okay? Because the propositional logic and predicate logic, things are very black and white, okay? It's either true or not true. Right? It's either true or false. And from a set of axioms, you can get to a theorem. But if you can prove a theorem, it is a sure thing. Okay, it is definitely true. And it's very mechanical. We talked about resolution. Okay, we talked about the resolution by refutation method. and it is a very mechanical kind of thing, and you just have to look for the symbols, cancel out, the non-negative version and the negative version of a variable, combine the rest into a disjunction, and so on. So it's kind of mechanical. Discrete probability is the beginning part of probability, and we'll talk about more about probability in this class as well. But this is the starting point. So the starting point is, why do we even care about probability? Now, with the other stuff, which is propositional logic and predicate logic, the reason why we study that has to do with automated theorem proving, which ultimately can lead to automated program verification. Okay, so that's why it is useful. But what about probability? I cannot use probability to prove an algorithm is correct. But there are other things that I can use probability to, not so much to prove, but to indicate, hey, what is the likelihood of that happening? Okay, so if I just kind of pump up the font size one more time, okay, this is easier. So the general notation is P of x equals y is denoting the likelihood, which is y, of the event x happening. Okay, that's general probability. It's not even just for discrete probability. But why do we want to know, or why is that important? Now, one thing is the bottom line is just money. Okay, so why would probability be related to money? The first one is if someone is placing a bet, okay, it might be helpful to first understand the likelihood of winning first before placing a bet. Is that making any sense? So if you're placing, if it cost $2 to place a bet, okay, the payoff is, let's say, $200. But the chances of actually winning with that bet is 1 in a million. Would you do it? Just the order of magnitude tells you it's not worth your time, right? It's not worth the $2. So even though $2 is not a whole lot of money, probability is against you. Okay, so the likelihood of you not winning is saying, oh, you're most likely going to lose that $2 instead of winning $200. Okay, but some people don't really care, even though they know the slim likelihood. They think they are particularly luckier than the rest of the population. So they would just ignore statistics completely and go like, I know I'm more lucky than the rest. So even though it's 1 in a million chance for other people, with me, it's more like 0.999. 99.9% of the chance. So there's no arguing against that sort of type of assessment. Okay, next one. What is the likelihood of a driver getting into a particular costly accident? And as a result, we have to determine the insurance premium accordingly. Is that making any sense? From the perspective of insurance companies, they have to study probability because they want to, they want to be able to set the premium of automobile insurance. What do you think is more expensive to insure? A minivan, which is super boring, associated with family, men or women, or a Miata, little two-seater, sportster, basically well known to be, people take it to the track, they race around in those things in parking lot Grand Prix, otherwise known as autocross. Okay. So which one do you think costs more to insure?
Yeah.
And I'm only talking about third party. Okay, so there's no insurance for the car itself because otherwise a more expensive car is going to be more expensive to insure. So we'll take that factor out completely. It's just all for third party. Which one? The van. Yes, you are absolutely right. The van is actually considerably more expensive to insure than a Miata or MX-5. Okay, why? Well, there are more passengers, but remember, I'm talking about third-party insurance here. So you're not even insuring
It's going to cause more damage. It's going to cause more damage.
It can cause more damage, and it's more likely to get into an accident as well. Now, that is strictly probability. Okay, they're just basically looking at 1,000 cases. Okay, of 1,000 cases, how many MX5s got involved in an accident and how many minivans got involved in accidents. Now it can be because of a variety of reasons. Okay, people who drive a minivan, they always have kids in the background, screaming, kicking, complaining, whining, okay, drinking, eating, arguing the whole time, and distract the driver. Okay, as opposed to Miatas, which you cannot have too many passengers, right? It's a two-seater, you get one passenger. And most of the time, even that passenger is missing entirely. So there's less opportunity to get distracted. Two, the handling is different, right? Now, it's granted minivans can be very fast, okay, but when it comes to handling, they're not exactly, the star of handling, right? So there's the other factor. So there are many factors determining, the likelihood of a particular kind of car driven by a particular kind of driver and into an accident. Now, there are minor accidents, there are major accidents, okay? Minor accidents, people get hurt, but not particularly costly to pay up. And then more major accidents, you have to pay a lot of money. So they have to factor all of that stuff in order to determine the premium, okay? Are there any questions about this part? Okay, so that's probability right there. When you take classes in science, in chemistry or physics, why do you spend so much time in the lab doing experiments? Well, your professors want you to look at the outcome of experiments, and you have to come up with a conclusion of whether the result of your experiments support a particular theory or not. Is that making sense or not? Okay. So here comes something that is not completely related to this class, but is sort of related. Do you think scientists know the truth? That is a very good statement. Okay. So the answer is no, scientists actually do not know the truth. Okay. They just know what cannot be proven wrong. That's all they know, is what cannot be proven wrong. Because that's the whole scientific spirit, is you have a theory and then you design experiments to show that nothing can be contrary to the theory. Yep.
I was just going to say, so every theory is technically a probability of just 99.9%.
It just cannot be proven wrong yet. Okay, but it can be proven to be consistent. Okay, that's the other part, is it can be proven to be consistent, but cannot be proven to be wrong yet. So if you think about Newtonian physics, okay, back in the 1800s, I think, okay, so at that time, because we did not have the ability to observe phenomena to suggest otherwise, so all the experiments are consistent, and they cannot prove Newton's theory wrong. Okay, they're all consistent with that theory. But once we have the ability to observe things that we could not observe before, now we can start to say, hey, that's not right. I mean, I can actually see light bending, okay, because of the sun and so on and so forth. And that's why, oh, okay, Newtonian physics is a good approximation, but it's not the truth, okay? It's just, good enough for most things. All right, so that's just a little sidetrack. This one is kind of interesting because I use it a lot when I still had multiple choice questions, is what is the likelihood of two answers to two multiple choice exams having identical wrong answers? So I'll have student A and student B turning in the answers of one particular exam. It's multiple choice, okay? Of all the wrong answers, let's say these two people have like 90% of the wrong answers being identically incorrect. So what is the likelihood of that compared to the likelihood of the rest of the class? If I just randomly pick two students in the same class and compare which questions they get wrong and how they got it wrong, how does that compare? Why do you think that is important to me?
So you can get feedback on your teaching.
I can get feedback from my teaching, but I can also identify potential cases of people just copying, right? Because this is especially important for an online class, okay, with online assessment. If you're taking a multiple choice test with D2L, okay? Nobody can actually see what the student is actually doing, right? So there's no no such thing as saying, oh, I can actually see that person copying the answer off of somebody else, okay? And they may not be using the same IP address, the time may not be the same, because now you can just take a cell phone, take a picture of a screen, and just text it along to somebody else, right? So now probability becomes more important because I can now say, well, the chances of this happening is really, 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 really slim, and use that as an argument and say, well, I have strong reasons to suspect that this answer was copied from the other person. So this is the conclusion of why we kind of want to study probability in a world of uncertainty, and you can just ask any quantum physics professor. How many people here has taken at least one class that touches on quantum physics? Okay, how did you like that class?
Chemistry.
Chemistry. Is it PChem, physical chem?
Just the Chem 400.
400. Okay, so that's just advanced chemistry. They have a PChem or physical chemistry class, maybe not here, but they talk a lot more about the quantum physics. What is the context of quantum physics in that class?
That was actually really interesting because the orbitals.
Yep.
Is
Yep.
there's only a what is it, like 90% chance probability that an electron can be found inside the orbital.
Yep. Yep. Okay. So think about a nucleus and the electrons that go around, quote unquote, goes around the nucleus. Okay. At least in the 60s, 70s, and 80s, okay, when people did not know a whole lot about quantum physics, they think of a nucleus. Okay, let's say this is a hydrogen atom. Okay, so you have a nucleus with a single proton, and then you have the electron on the outside, right? So this is a proton with a positive charge. This is an electron with a negative charge. Most people think about this and go like, oh, this is the same thing as Earth and the Moon, and the electron just goes around in an orbit like that. That, unfortunately, is not the case. First of all, there's no such thing as a line orbit, okay? It is more like a sphere. So the electron is actually, quote unquote, in an orbit that's more like a 3D sphere around the center, which is the proton. How do you make an orbit out of a sphere? An orbit is always like this, right? It spans a two-dimensional space, not a three-dimensional surface. It doesn't help, right? And then you get into orbitals that are of really strange shapes. I think this is the p orbital. This is the s orbital. The p orbital is the one where you have the nucleus in the center, and then the orbit looks like this. You have basically two teardrop thing on each side of the nucleus. How does an electron orbit with something that looks like this? It is almost disjoint. It does not. Okay? So quantum physics says the probability of an electron appearing in this three-dimensional space is distributed according to a math equation. That's it. Okay? You say which part of the 3D space, it will return the probability. Okay? And electrons do not actually move. They just appear from one side to the other side, just like that. It does not have actual continuous motion. So once again, it is all about probability. It's no longer a Newtonian type of motion. It is just the chances of where it's going to appear next. And if you study more about quantum physics, eventually people will believe in banging their head on a wall, because there's a very slim chance that you can actually get through. It's very, 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 very slim, but nonetheless, there is a chance that people can just keep banging their head on the wall and actually get through. I have not known anyone who has succeeded, which is not to challenge you to try. Not the same thing. So the last part is, this is the best we can do, okay? Because, not counting spiritual, religious, or medicinal ways of dealing with reality. All right, so the next topic is talking about what is so discrete. Why do we call discrete probability discrete probability? Okay. So it starts off with the probability of something. Discrete probability deals with something that is not continuous. Because you're in this class, you must have taken pre-calculus already. And in pre-calculus, you deal with continuous stuff. What is continuous in mathematics? If I give you a particular set that is supposed to be continuous, what is a property of that set? Not the property, but just a property of that set. So we'll say, the real number, okay, the set of the real number. It's continuous. Why is it continuous?
No matter what two numbers you pick, you can find a number between them.
If you pick two different numbers to begin with, there's always another number between them. You're absolutely correct. So if I pick, x and y, both elements in R, if x does not equal to y, that implies that I must have another value z in R, so that z is different from x, it's different from y, but it's in between. Okay, so that's the whole nature of continuous, being continuous. Discrete means it's not continuous. Okay, that really is just the opposite of being continuous. So I give you two examples here. Okay, the first example is what is the likelihood of the highest temperature of today will at least get to 68 degrees Fahrenheit. Okay, as opposed to the highest temperature, what is the probability of the high temperature of today reaching 72 degrees Fahrenheit? Okay, that's actually continuous, because what about 70? It's right in between, right? And then you look at 68 and 70, 69 is in between. You look at 68 and 69, 68.5 is in between. So no matter which two different temperatures you pick, there's always one in between, and that's why in this case, that probability is not discrete, it is actually continuous. On the other hand, if your question is getting two or more tails in 5 coin flips, that is discrete, okay? Because there's nothing in between getting 2 or more tails and getting 3 or more tails. You cannot get 2.5 tails out of 5 coin flips. So that means it is discrete because it is not continuous. Okay? Are there any questions so far about discrete versus continuous probability? And which one do you think is more applicable in computer science? Discrete. Discrete is by far more applicable because computers are discrete to begin with. All right.
Because of memory constraints?
Because of the way we represent things, because we have digital computers, and with digital computers, it means everything is quantized or digitized already. And if it is digitized, you really do not have anything that can be continuous. So even when we look at double precision floating point number, it's an approximation of something that is continuous, but it is not actually continuous. At some point, you will not be able to find a different value between two distinct values, because there's no way to represent that particular point anymore. You run out of precision, basically. All right.
Yeah, approximation. It's all approximation and memory conservation.
Yeah, because we want to be able to allocate a fixed number of bits to represent numbers that are by its very nature continuous. So it's all about just approximation.
Basically mapping continuous numbers to a system that doesn't have a continuous value.
Yep. Because of pragmatic consideration. All right, so the next slide talks about discrete probability space, and there's a little bit of symbolism here, so there's a little bit more abstract stuff. When we talk about probability space, okay, whether it's continuous or discrete, it is still the same here. We have to talk about 3 different constructs. The first construct, which is omega, is kind of, well, it's not the same as the omega in propositional logic. This one is the set of all possible outcomes of the things that you're modeling. Okay, and later on we have an example of something that some people may be interested in. And then F is a set of events, and in this particular case, an event which is an element in F is a subset of elements in omega. That means it can be an empty set as well. Okay, because an empty set is a subset of omega, of any set. It can be the entire omega. So each element itself is a subset. In some cases, it can be a power set. Okay. In other words, F can be a power set of omega because a power set is the set of all possible subsets of a particular set. P is just a function. It maps elements in F, not in omega, to 0 to 1 inclusively. In other words, it maps F to a real number starting from 0 and ending with 1. And that's your probability function. Are we still doing okay so far with this? Okay. So the example that I have here is buying a lotto ticket. So in the case of a lotto ticket, omega is going to be all the possible combinations of the lucky number. So that's the entire space. Those are all the discrete possibilities out of buying a lotto ticket. F is a little bit tricky in this case because it depends on how you want to play the game. If you are only interested in the probability of buying a single ticket, then we are only considering singleton elements in F. So this is probably a good way to represent it. I'll just go ahead and give you the exact example. So, okay. So in the case of Lotto, okay, this is Lotto, and we'll say this is a Powerball, okay, the Powerball version of Lotto. Okay. So in this case, omega, I have to spell omega because I cannot type the omega symbol here. So omega will be a set of all possible combinations of the lucky number and then plus one Powerball number. Okay. So we have, I'm just giving you an example here. 1, 2, 3, 4, 5, as the lucky number, and then plus 1 as the Powerball number. The Powerball number is independent from the lucky number, so the same number can be a part of the lucky number and also can be the Powerball number at the same time. The next one is going to be 1, 2, 3, 4, 5, which is the lucky number plus the Powerball number of 2, and so on. And I think the last one is going to be 59, 58, because you can pick from 1 to 59 for the lucky number. So it's 59, 58, 57, 56, 55, with a Powerball number which is only going from 1 to 35. So 35 is the last one. So there are a lot of elements in omega. Are we doing okay so far with the meaning of omega? It is the set of all possible outcomes. Okay. Now the set F is a little bit different. Okay. F is each element of F is a subset of omega. So how you want to deal with F depends on how you want to play the game. If you're only interested in buying a single ticket, then the F would only be singleton sets. Okay, so it'll be each element of F is by itself a set, but each set only has one element from omega. So it would just be this, and that's one set already, and it goes all the way to the last one, which is a set of the last combination of numbers.
Someone's happy.
Someone just won the lotto.
Wait.
If I ever won the lotto, nobody's gonna know about it.
No one will ever see you again.
Except I just, hey, what about cisp440? How come Tack is not in class today? And there's no notice on the door either, right?
And then a robot shows up.
To replay all the videos from the past.
Exactly.
Yep. All right. So F is not the same as omega. F is each element of F is a set of elements from omega. Okay. So in this case, I'm modeling the way of playing Powerball Lotto by saying I'm only interested in buying one ticket at a time. What if I'm interested in buying 2 tickets at a time? Well, then each set will have 2 elements, and each element being an element from omega. Is that making any sense? So now, when we look at P, So P is going to be applied. P is a function that maps F, which is our domain, to the codomain of 0 to 1. What is the probability of any element within this set, happening? That is the question. That is, how P is formatted. Are there any questions about these three components of a probability space? Okay, so you start off with all the possible outcomes, and then you create subsets of the outcomes that you're interested in, and then you define the probability to map from each possible outcome, event, to the probability. And by the way, each one of these is called an event. A set of elements from omega is called an event. So an event can be nothing, can be exactly just one possible outcome, can also be multiple possible outcomes. It all depends on what your problem is and how you want to model that particular thing. All right. So are there any questions about this example of what is the omega, what is F, which is the set of all events, and what is P, which maps events to the probability of the event happening? No questions? All right. Well, if there are no questions, we'll kind of move forward and we'll start to talk about something that is a little bit more interesting. It is about combinations and permutations. And this is going to be the core part of today's lecture. The previous half hour is really kind of more like the introduction to probabilities. And this is the fun part of probability. It's about, gambling has a lot to do with combinations and permutations. Anytime you play, you have playing cards, it's all about combinations and permutations. Okay. But in this case, I'm going to use a very simple example, which is Lotto. Okay. So we'll go to the Lotto app website first to thank California Lotto for raising money for community colleges in California. No, I'm just kidding. That is actually the case, but I do not. Well, okay, I'm not going to say anything. I'm just going to calculate the probabilities.
It's a tax for the poor.
Hmm?
Oh, no. Tax for the people who can't do that.
I think that's the general consensus, Okay. So we'll go with, just Powerball, and you can see how many different ways you can play Lotto. So we'll go for Powerball. And now when you look at, this website, it already gives you an FAQ. Let's see, where is the FAQ? Right here. All right, so when let's click on how to play. So the how to play part, tells you the rules of the game. And if I just zoom in a little bit so we can all read, in case we don't know how to play Powerball. How many people have bought at least a Lotto ticket? Okay, well that's okay. Okay, I have never bought a single Lotto ticket, so I don't know. Until I read it on the website, I really don't know anything about playing Lotto. All right, so how to play Lotto? Find a Powerball retailer. Okay, fine, we can ignore that part. But as far as we are concerned, this is the important part. How to pick. Pick 5 lucky numbers from 1 to 59. Okay, so when it says pick lucky numbers from 1 to 59, each number can only be picked once. So you cannot say, oh, 7 is my lucky number. I'm going to pick 77777. That doesn't work. Okay, so each number can only be picked once, because once that number is picked, it cannot happen again because of the way they draw the lottery. Okay, because they put like 59 balls into a cage, I guess, and then they pick out basically 5 balls in this case, and then use those 5 balls to form the lucky number. So that's why the same number can never occur twice. But the Powerball is different. The Powerball is independent. If I understand this correctly, it is independent to the first 5 numbers, and as a result, the same number can appear again as a Powerball number. Is that correct? Okay. All right. Or play randomly generated number with quick pick. You may select up to 5 additional quick pick plays on each play slip, and you may play as many play slips as you like, blah, 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 blah. Okay. So the bottom line to us is, from the mathematical perspective, is you're picking 5 items out of 59, and then plus 1 out of 35. So we want to calculate at least how many possible tickets, unique tickets, are there with Powerball Lotto. Now I know most of you will say, oh, I read this whole page, that number is already at the bottom of this page. But I wouldn't trust that number. Okay, I would come up with that number by myself using my own calculations. Okay, so we want to do some calculations here. And to do this calculation, we have to rely on some really useful concept in computer science and in probability. It's called combinations and permutations. But before we talk about that, it is kind of important to talk about factorial. How many people do not know what is factorial? Okay, so let me ask you in a different way. What is 4 factorial? 4 times 3 times 2 times 1. Okay, very good. So factorial is nothing more than the product of a whole bunch of numbers. So when I say n factorial, one way to look at this is it is the product of I going from 1 to n. Okay, that's one way to look at n factorial. Do you guys know this symbol? The product, instead of a summation, a sigma, this is the product of all the terms. In this case, each term is just I, and I goes from 1 to n. So that's one way to write the closed form of otherwise known as n times n minus 1 times blah, 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 down to 1. Okay, that's just n factorial. Okay. And factorial itself is very useful. Okay, just by itself is already useful because it's telling you how many permutations you have when you have to arrange n things. Okay. Some of you have encountered this example before because when I taught CISP 300, I would use this as an example. Okay. So if you are a pizza delivery driver, okay, and you have, let's say, 5 stops to make, how many ways can you arrange your route so that you will traverse all 5 stops and end up at the same point? Well, let's make it easier. Let's say you have 3 stops because I can quite easily enumerate all permutations. So you have stop A, B, and C, and this is the pizza place. Okay. So just from the map, it doesn't seem very obvious you have to traverse in a particular way to save fuel because they're all kind of about equal distance from the pizza place. Okay. So in order to determine which one is your best or the optimal route in terms of your fuel, time, and etc., you kind of have to consider all possible ways to traverse these 3 points, right? And we don't have to consider traversing the same point twice because that would just not be making any sense. So the 3 ways to do it, or the 6 ways to do this, is to start with A. Okay, so I would consider starting with A first. But if my first stop is A, what about the second stop? Do I have to reconsider A as the second stop? No, the second stop can either be C, B, or C, right? So let's say I pick B as the second one. Once I have picked out the first 2 stops and I only have 3 stops to begin with, what is the last one? It's got to be C. Okay, fine. And the next one is starting with A again, but the second stop, instead of B, I can now choose C. But once I have chosen A and C as the first 2 stops, the last one has got to be B. Now I have exhausted all the permutations starting with A. I move on to B. BAC is one, BCA is another one. Now I have exhausted all the routes that start with A and B, so I can start with C. CAB and CBA. That's it. These are the 6 possible permutations of arranging 3 destinations. Permutation means the ordering is important. So ABC is considered different from ACB if they are considered distinct possibilities. Are we doing okay so far with this? 6 is 3 factorial because it's 3 times 2 times 1. what if you have 4 stops with your pizza delivery route? Then how many possibilities, how many ways can you arrange the destinations? Then you have 4 factorial, which is 4 times 3 factorial, which is 24. Okay? What about 5 stops? That'd be 5 times 4 factorial, which is 5 times 24, which is 120. So you can see how that number increases rather quickly. Right? 3 factorial is only 6. 4 factorial, 24. 5 factorial, 120. 6 factorial, 720, and so on. Okay? Now with pizza delivery, you probably won't have any more than what, 4 or 5 stops at the most. But what about UPS? How many stops do you think a typical day for a typical UPS driver, how many stops do you think that driver has to stop?
100.
Just give me an order of magnitude. I used to have a student who worked for FedEx or UPS. Just give me an order of magnitude.
200.
200?
100. Yeah.
Okay, so 200 stops, okay? So assuming that 200 stops are somewhat random and you cannot really just visually look at those 200 and go like, oh, they're all in a straight line and figure out that. That's how I'm gonna do it. What is 200 factorial?
Really big.
A really, really, really big number, right? In fact, we can probably look it up and find out exactly how big of a number we're dealing with here. 200 factorial is this number here. Let me just magnify the screen here. So it's about 8 times 10 to the power of 374. Okay, so I don't even care about the mantissa. It's the order of magnitude. It's the times 10 to the power of 374 that bothers me. Okay, so this means if you can come up with a quick algorithm to optimize the path for a pizza truck or pizza delivery, it's not going to work for UPS or FedEx. It does not scale up. Okay, so this is just one interesting fact about factorial is it grows faster than the exponent. Okay, you pick any base. Okay, you pick any base, and say I'm going to raise it to the power of n. This is pretty fast. Okay, if you look at if you plot out this function, it does increase pretty rapidly, but not as rapidly as n factorial. Okay, in the long run, n factorial is faster than any number to the power of n. Is that all right? Okay. So with that out of the way, we're coming back to the Lotto idea, the Lotto problem. Okay, so now that we know how to create permutations, what about lottos? Okay, so I'm not going to enumerate all possible cases, obviously, but if I pick out, if in the process of Lotto, the first number that is picked out is 1, then the second number cannot be 1 anymore. It can only be 2 all the way up to 59. Is that making any sense? Okay. So 1, 2, 3, 4, 5 is a possible lucky number, the combination. Permutation, I should say, permutation. And 1 can be the power order. Okay. So, but when you look at this, how many choices do I have for the first number? It's picking 1 out of 59. So I have all 59 possible choices for the first number. Okay. The second number, since I have picked out 1 already, so I only have 58 balls left in the cage. So I only have 58 possibilities. The third one, I only have 57, 56, and 55. So now if I multiply these numbers, 59, 58, 57, 56, and 55, the product of all of these numbers becomes the number of permutations of choosing 5 items out of 59. Is that okay? Any questions about the number of permutations in this case? So the number of permutations can be denoted like this. Uppercase T, the number of items of which we are choosing 5. This, in this case, it is 59 times everything all the way down to 55, which is not a very nice closed form equation, which I don't like. Can we arrange this a little bit differently so that we can make a closed form of this without using the dot dot dots? Can I use factorial in this case? What do you guys think? Okay, so we're looking at the permutation of choosing 5 out of 59 objects. We know this is 59 times 58 times 57 times 56 times 55. Do you think it might be doable using factorial? Let's think about it. 59 factorial. But tag, 59 factorial has a whole bunch of stuff that we don't want, okay? Because in addition to 59 multiplying all the way down to 55, it also has 54 times 53 times 52 all the way down to 1. But when you look at the extra component that we have in 59 factorial, that thing by itself is a factorial as well. Whose factorial are we talking about?
0. 55. 0.
Hmm? No. It's 54 factorial. Think about it. Is that making any sense? Okay, let's spell this out and see whether it makes any sense. Okay. 59 factorial is 59 times 58 times 57 times 56 times 55 times 54 factorial. Right? Because 54 factorial is 54 times 53 all the way down to 1. So if I divide this, and divide it on the other side as well, with 54 factorial, what do I get? The 54 factorial cancels out. Right? So now we only get the permutation. We get this number back, which is the permutation, the number of permutations of given 59 objects choosing 5. Is that working out okay or not?
Because you can only choose 5 of them.
Because we can only choose 5, right? But the Lotto game is not based on permutations, okay? So that means if the number drawn is 1, 2, 3, 4, 5, as opposed to 5, 4, 3, 2, 1, it's considered the same in the Lotto game. So permutation is not taken into consideration. It's only the combination. Is that right or not? What does a form look like? What does a Lotto ticket look like? Does it give you the ability to choose the ordering of the numbers? I don't think so.
Depends on how you buy it. If you buy it randomly generated, no. If you pick yourself, though, yeah.
Okay, but if you buy it randomly, it's sorted, right?
Right.
So that means they do not consider ordering important, because
Right.
otherwise you'll be seeing different permutations of the same 5 numbers.
Basically, when they pick the numbers, as long as you have the 4 numbers or the 5 numbers in the power.
Exactly. Yep, exactly. So in the game of Lotto, this is not the number that I need. Okay, it's a good starting point, but it's not what I need. Okay, because even though I have picked out the 5 numbers, I'm going to use another color here to indicate the 5 numbers that I have chosen. Okay, so A, B, C, D, E. So I'm not even using the actual numbers here. If I have 5 unique numbers, A, B, C, D, E, this permutation, as far as the Lotto game is concerned, is equivalent to B, A, C, D, E, which is equivalent to all other permutations given these 5 numbers. Are we doing okay so far with this concept? Okay. In order to win the Lotto, you only have to pick out the same 5 numbers, but the ordering is not important. Good? It's not important.
So for example, if you have 5 numbers, you're gonna have all the combinations, and you're gonna have all the winners, like any combination of that 5 numbers.
Any permutations of the number. Any way you order these 5 numbers is okay. It's considered the same. Okay? But how many ways can I rearrange 5 things? Chad, you haven't talked about that before. Wait, I did, right? That's permutation. That's the permutation of choosing 5 out of 5 items. I got 5 choices for the first one, 4 choices for the second one, 3 choices for the third, 2 choices for the second last, and the last one is no choice because it's the leftover. So in this case, it's 5, 4, 3, 2, 1, which is 5 factorial. So what this means is for each combination, there are 5 factorial permutations. So when you look at the total number of permutations, you have to divide that by 5 factorial. That gives you the number of combinations. Is that doing okay or not? Okay. So that means the number of combinations is the number of permutations, in this case, divided by 5 factorial. So when I look at this whole thing, okay, the number of combinations, which is an uppercase C with 59 on top and 5 down here, it is this number, which is P 59, 5 divided by 5 factorial. If you expand all the terms, it becomes 59 factorial. Here. So it becomes 59 factorial divided by 5 factorial times 54 factorial. Are we doing okay or not? This part comes from P59 5. Are there any questions at this point? Because I see some questions. I see some expressions that indicates there are questions. No questions? Yep, go ahead.
So you divide by the 5 factorial because permutation does not matter.
Because ordering does not matter. That is correct. Yep. When you count permutations, it will be 59 factorial divided by 54 factorial. But because there are 5 factorial permutations per combination, and I only want to count combinations, that's why I have to divide all the permutations by 5 factorial. Because once you have, once you're only considering 5 unique numbers, you have picked out the 5 numbers. There are 120 ways to arrange those 5 particular numbers. That's why we have to divide the 5 factorial. So in general, okay, not in this, not specifically, but in general, the equation of calculating the number of combinations, there are 2 notations commonly used. This is one way to do it. Okay, keep using 59. So if you're choosing R objects out of N, which is also known as C and R, okay? They're basically the same thing, just different notations. This indicates the number of combinations choosing R out of N objects. That is N factorial divided by R factorial times N minus R factorial. Are there any questions? This is just a generalization of what we have talked about. I was using Lotto as an example so that we can actually see the numbers. All right, so let's go ahead and take a look at binomial formula. X plus y to the power of something. So we'll take a look at x plus y to the power of, let's say, 2. How many x squared do we get? How many xy do we get? 2. And how many y squared do we get? Just 1. Right? Okay, very good. And I'm going to erase this part here. What about x plus y to the power of 3? How many x cubed do we get? Just 1. What about x squared y? How many of those do we get? We have 3 of those, okay? What about y squared? 3 of those, and then 1 y cubed. Okay? Okay, let's go to the next one. X plus y to the power of 4. We only got one x to the power 4. That's still easy. What about how many x cubed y do we get? 4 of those. What about x squared, y squared? 6. There are 6 of those, and then 4 again, and then 1 again. Okay. Do you see a particular pattern here? What do you think is going to be the next one? Okay. If you just write out these numbers as a triangle, you will start to notice a pattern.
Talking about Pascal's
Yep.
triangle.
This is Pascal's triangle. So we have 1, and then we have 1, 1, 1, 2, 1, 1, 3, 3, 1, and then we have 1, 4, 6, 4, 1. And this will make a really good programmer's aptitude test for IBM. What is going to be the next row? 1, 5, 10, 10, 5, and 1. And why do you think this might have something to do with what we are talking about?
That's the CI.
That's the C, yep, that's the number of combinations. The combination of choosing 0 item, the number of combination of choosing 1 item, 2, 3, 4, and 5. So the row number indicates the n, and then on the same row, when you sweep from the left-hand side to the right-hand side, it doesn't matter because it's all symmetric. That's your arc, starting with 1, ending with n itself. Isn't that kind of interesting? Because you can do all this with only addition. You don't even need multiplication to calculate the combination, the number of combinations. So, okay, let me just be clear what I mean by here. Okay, so this is n equals to 1, n equals to 2, n equals to 3, n equals to 4. Oops, take it back.
First one is 0.
Yeah, I'm off by 1. 1, 2, 3.
It should be n equals 0, 8
The
equals,
first one is 0.
8 equals 1, 8 equals 2. Yay.
Yep.
I've heard of Pascal's triangle, but what is it used for? What is it used for, Pascal's triangle?
Well, combinations has a very useful application. When you have think about flipping a coin. Okay, and this is not a loaded coin. It's just a normal coin. You have 50-50 chance landing on the head or the tail. Okay, so if you try to plot out, given that you have n flips, okay, if you try to plot out the frequencies of or the expected probability of having 0 tail, 1 tail, 2 tails, 3 tails, and so on, that probability has to do with these numbers. Okay, think of x as head and y as tail. When you go all the way back to the binomial formula, think of x as head, think of y as tail. Then when you have 4x cubed y, it means the frequency is you have 4 times that you will get 3 heads and 1 tail. Is that okay?
Mm-hmm.
So when you have when you consider n equals to a really large number, let's say 100, okay? Then it is equivalent of saying, okay, I have 100 coin flips, and each number of this row is telling you what is the frequency, the relative frequency of having 1 head, 2 heads, and so on. It's actually 0 head, 1 head, and so on. Okay, because it starts with 0.
I don't really see how that relates to the triangle, though. Yeah. Oh, I guess because the formula. That's right. Okay, I think I got it now. Thank you.
Okay. So that's why binomial or Pascal's triangle ultimately has a lot to do with the distribution. It's also when n becomes really really large, okay, it becomes the normal curve in statistics. Well, we'll talk about the normal curve later on, okay? But that's that's in general continuous statistics, not discrete. All right. So we have our basic number now because we have the number which is 59 factorial divided by, so the combination, the number of combinations of choosing 5 things out of 59 is 59 factorial divided by 54 factorial times the factorial of 5. Okay. But we also have the Powerball, okay? Don't forget the Powerball, which is completely independent to the lucky numbers. So that means the actual number of possible outcomes in the case of Super Bowl, the Powerball Lotto, is going to be this number times 35. All right? So now we'll go ahead and try to calculate this one. I'm not sure whether my calculator can deal with that number. We'll give it a try. Okay, so we'll go to advanced mode. And we'll say we want to calculate 59 factorial divided by the product of 54 factorial and 5 factorial. And then we want to multiply this whole thing to 35. And it does come up with a number. And the question is that the number that the Lotto site is quoting? So we scroll down. Believe. Oh yeah, I like that step forward right there. Yep. And I think it comes up with the odds too. There we go. So the odds, which is 1 in a number, I think that is exactly the number that we came up with. Yep, there we go. So we just verified the information on the Lotto site. So when is a good time to buy a single ticket of Lotto?
After 1 million.
When the payoff is that much? Well, what about Uncle Sam? When you win the Lotto, it counts as your income.
25%.
If you take a lump sum of that much money, what is the tax rate?
You have an initial tax though of the lump sum of 25, and then you have to pay income taxes on what you actually, the rest of what you got.
Yes, and that the tax rate combining your state and federal is about what? Half?
Above $250,000, the tax rate's only like 33%.
So you need to take that into consideration. What about multiple people getting the same, picking the same numbers? That's possible. Okay, the Lotto doesn't say anything about oh, we'll only issue 1 ticket per possible outcome. Okay, per possible outcome, they can issue as many tickets as there are people who are buying. Yep.
So now that we know the probability of, or the odds of winning power, basically Lotto, what are the odds of having multiple winners?
That's a good question because it depends on the jackpot. Okay, so if we go back to Powerball,
Let's just assume that everybody in the country buys one. Well, say everybody in the country buys 1 ticket just to make it
okay,
simple.
that's about 300 million.
Yeah, 330 million.
Okay, fine.
Okay. So how would you figure out that probability?
Then the probability is you have about 2 people buying the same ticket. Because 330 million is approximately 170 million times 2, okay, give or take a little bit. So if the probability, if it's all random, okay, if everybody's just saying, okay, I'm just picking random, and not a whole bunch of people saying, oh, okay, now certain things can skew that probability, okay. If you go to a Chinese restaurant and you get a fortune cookie, and now they have a lot of like this is your lucky number thing, okay. So what if the fortune cookies always use the same number? Then you have a probability of having more people to pick that number than all the other numbers. So they may be skewed to that particular number, in the fortune cookie. So assuming that is not the case, everything is random, then on the average, out of 340 million tickets issued, then you may have 2 tickets of the same. Is that making any sense? So that means, you know, the jackpot will not have to be split between two winners of the two winners, and each person is only getting half of the jackpot. Okay. So what are the chances of that happening? Pretty high. Okay, because when the jackpot is a lot of money, most people will think in the same fashion and go like, oh, the jackpot is pretty good. I mean, you know, the chances of me actually winning is pretty good. So more people will tend to buy more tickets, and as a result, you know, they can potentially issue more tickets than there are unique number combinations in this case. And there are multiple cases already. I mean, there are many, many cases where, you know, when the jackpot is really high, they have multiple people, you know, who have to split the jackpot. What is the current jackpot? You can actually see it. I mean, the FAQ has, what is the Powerball? Ah, that's too hard to find. Powerball jackpot.
Yeah, we got Google. Why are we doing this?
Yeah. Okay. Okay, I guess that would be the one. 33 million. Okay, current estimated jackpot is only $50 million. And you have 1 in 170 million chance to win. So the chances of winning is less than 1 in 3. I mean, the payoff, the average payoff is 33 cents per dollar.
What determines the jackpot? Is it like how many people play? Like the more people play, the higher the
I think it's a
jackpot.
cumulative thing. It's like how much
Time
money
since
they have saved over time.
Time since the last time someone won a
Right.
jackpot.
Yep. Yep.
So
So there you go. Yep.
let's just assume for a second that the jackpot's like 300 million.
Mm-hmm.
And so if you bought, you know, how many tickets there are? So 175 million and some change tickets.
Mm-hmm.
Like if they were $1 a piece, technically it'd be worth it.
Correct. If you
Yeah.
buy a lot of tickets, then it's worth it. Yep. If you buy 100 tickets, then your chances of winning is now 100-fold of buying a single ticket. Assuming those 100 tickets are all different, right? Because if you buy 100 tickets, all of the same numbers, then it's not going to be very helpful. Thank you for your donation, sir.
Isn't there a way to there's a way to generate random permutations non-unique, correct?
Yeah.
Or random combinations non-unique.
Yeah.
Programmatically.
In fact, that would make a really kind of nice homework assignment that you can do in half an hour. Write a program that can generate, you know, all permutations of the Powerball Lotto.
Is that really actually a homework assignment?
And you can use scripting languages, because to do this in C is actually more troublesome than it is worth when you do it in Perl or PHP, because they do have the concept of a list, okay? And you don't have to implement your own list. It's so much easier because you can just say, you know, pick one item, pick the nth item from the list, and remove that item from the list, and then you move on to the next one. That makes it so much easier to deal with knowing which number is already picked out. Are there any other questions about the concept of combination, permutation, and Powerball Lotto?
Is it against the rules to pool?
Huh? Nope, it is not.
Oh, really? So you actually have like a group of like 1,000 people like drop like $50?
Oh yeah. Oh
in it?
yes. Absolutely.
Wow.
Does anyone work for the state here? No. Even if you did, you do not want to raise your hand, because they regularly arrange pools like that.
Oh.
Okay, when the jackpot is high, you will end up with like the whole office, the whole division of something, you know, pooling the money together and buy like 1,000 tickets or something
Happened
like
a
that.
couple years ago, in fact. They
Yep.
won like $315 million.
Yep. But then the question is still, is it worth it or not, right?
Well, there's also the legality of it. Whoever actually buys the ticket, someone is technically entitled to the prize.
That is correct.
Yeah.
Yeah, but with the state workers, they all know where each other lives, so there's
We'll
that.
find you.
So there's that.
You're gonna be like Liam Neeson your ass or something.
Yeah, something like that.
There was a guy who did like an office pool, and then one day he decided not to play, and that's the day they all won.
Oh,
And he tried
wow.
to sue them, saying like, I bought the tickets every other day, just that one day I missed.
Too bad, guy.
Yeah.
Too bad.
Okay, so the rest of this slide is really the same stuff that we have talked about, except for this one, which is the reciprocal of 175 million something. That's basically the probability of winning if you just buy one single ticket. That's the chance of winning if you just buy one ticket, which is pretty small. Hmm? Which is pretty small.
5 times 10 to the negative 7th percent.
Yep.
That is small.
Okay, so the next question is, what if you never played Lotto? Okay, why would you still be interested in probability or combinations or permutations or anything like that? So I have to reorder the topics a little bit. So I'll go to this one first, about frequencies and probabilities, and that has to do with what you just mentioned, okay, about binomial stuff and why does it have anything to do with probability? Okay. So it's not in here, but I'm going to talk about it in this here. Okay. So let's say you want to toss a coin 1,000 times. Okay. So 1,000 coin tosses. Okay. And I want to plot out the frequencies of how many times I would end up with 1 head, 2 heads, 3 heads, and so on. Okay. What do you think that curve would look like out of 1,000? So this is going from 1 to 1,000, and it's just counting the number of times that head comes up, with a coin toss. And this axis is indicating frequency.
Like a sine wave? Like a sine wave?
No. Well, you can kind of say it's a sine wave, but it's not a sine wave. It's not cyclical for one thing. Okay. But first of all, which number is going to have the highest frequency? In other words, most of the time, out of the rest, we end up with this number of heads versus, the other number being the tails.
500.
500, right? So 500 is going to end up being the largest number. So the curve would basically look like this. Is your typical normal distribution bell curve. Except it is still discrete, because when you look at each column, it is still an integer, okay? Because it's just telling you how many times you end up with that. But how is that related to binomial equations? Because when you look at x plus y to the power of 1,000, that frequency, this frequency here, is basically the number that you have x to the power of 500 times y to the power of 500. Okay? So when you have a normal distribution, it's kind of like a continuous version of the binomial distribution. You basically have a symmetric curve, still bell curve shaped, except you have a it just stretches out to infinity on one side and stretches out to infinity on the other side, and in the middle it will still be the highest frequency. Okay, so that's why frequency is important, because it tells us about the distribution of probability. When you add up the entire area, what do you get?
Number of heads you got.
Well, let's see if we can come up with a certain closed form here. When I add up all the numbers on one row, we have 1, 2, this is 4, this is 8, and that's what?
16.
16.
It's 2 to the power of n, isn't it?
Yep. So that means when you add up the frequencies of everything here, the area under this curve is going to be 2 to the power of 1,000. So the relative probability of having exactly 500 head and 500 tail is going to be that number divided by this. So that's basically out of 1,000 items, selecting 5. Yep. That would be the probability of ending up with exactly 1/2 of head and the other half being tail. Is that okay? Yep, go ahead.
2 to the n, is that the cardinality of the power set?
Yep.
Omega.
That is the number of power sets as well. Yep, exactly. That's the reason. Okay, are there any other questions? Each element in a power set, is it representing a combination of elements or is it representing a permutation of elements?
Combination.
Combination, exactly, because ordering does not matter. Right.
So the coin flip is kind of a good analogy for computers, right? Because zeros and ones.
Mhm.
You only have either 0 or 1.
Well, this is useful in many opportunities. So I'm just going to give you one particular one, which is the previous slide, which is discrete probability and computer security. You can read about it later on, but I'm just going to describe what is the general idea. Okay. So how do you make sure that your computer is secure? Now, what is computer security, by the way? Since you guys are all in the computer science major, you should have some idea of what is considered a secure computer. What is an insecure computer? Let me ask you the other side.
Unprotected.
Unprotected, and it can be compromised, right? It can be hacked, can get infected, can be used to launch attacks on other computers. You may lose information, okay? Whatever you store on that computer can be lost. Somebody can put other files onto your system unauthorized, okay, in an unauthorized way. How do you protect your computer? You run what? A virus checker, okay? Sorry? Linux, okay, but Linux can be infected as well, okay, but by the time you run a virus checker and it comes back with an infection, it's too late already, okay, the damage has been done, okay, is that making any sense? So the question is, are there any ways to spot problems or potential problems before they happen?
Hacking.
Now, most of the hacking starts with some sort of intrusion, right? Somebody is trying to get into your computer without, your knowing or your authorization. So how do you know that somebody is trying to do something like that? And once they get in, okay, how can you differentiate, before they plant anything in your system that can be scanned or detected otherwise, how can you tell that somebody else is in your system, somebody other than you is using that computer?
Packet sniffing. Packet sniffing.
Packet sniffing?
Or packet.
So you basically
inspection.
want to track the origin of that packet and see if that person is logging in from, let's say, a foreign country that you never planned to be in.
Or what requests they make, what protocols they're using to try to
What
make
protocol
requests.
they use? Okay, but all of that is not sufficient because let's say that person uses a school IP address and is using SSH to connect to your system. But let's say you do that regularly to do your homework too. So you cannot really differentiate between, is that me doing it or is it somebody else pretending to be me, somehow got my password and hacked
After
into my
like
system.
50 incorrect tries.
Okay, but if that's what if that someone is using a camcorder to record your your password, right? So what about when we type? Do you think the way you type and the way I type would be identical? Okay, when I type this, okay, uppercase THIS, okay, which is a fairly common beginning of a sentence, the timing between THIS, do you think that is universal to all people? What about typing mistakes? We all make typing mistakes, right? Do you think we all make the same typing mistakes as with the same frequency, with the same relative frequency? No, we all have unique mistakes and unique way of typing, and that has to do with everything else that we do. Okay, it has to do, doesn't really have to do with that much with the keyboard. If you play sports, okay, for instance, you might have certain ways of using your fingers and type in a certain way as a result. Okay, if you play the piano, okay, you might type in a certain way because of that training. If you play the flute, you might type on the keyboard in a certain way because of that training. So that's why the typing pattern is all kind of unique. The timing is unique, as well as the typing mistakes that we tend to make. So what if your computer is to keep track of all of that stuff? Okay, knowing that you are still you, okay, the user is actually you, it will keep track of your typing habit and keep track of your frequencies of mistake. Okay, I tend to type you instead of I because on the keyboard they're right next to each other, and the frequency is this compared to the frequency of mistyping A versus S on the other side of the keyboard. Okay, do you think that might be useful for intrusion detection? If someone else is to log into the system and but the typing pattern is completely different, or the type of mistake, the type of command, and the timing between the keys are all different from the usual, that would be a good signal and say, hey, maybe something is not right here. Is that right? But I don't have any solid proof that somebody else is in the system. Okay, it's not based on the result of a virus scan or a rootkit scan or anything like that. This is all about probability. And that's why probability is really useful, even in the case of computer security, because a lot of times, by the time you have solid evidence that somebody else has infected the system or has stolen information in the system, it's already too late. The probability can basically help you identify cases where, well, I guess it is still possible that we have a legitimate user on the system, but the probability of that is really, really slim. And that will give you reasons to shut down the system, at least, okay, to say, okay, something doesn't seem right, okay, it is worth the cost of shutting down the system just to take a closer look and see whether something is fishy or not. Okay? Are there any other questions? But why do I want to know about computer security? That doesn't seem related to what I want to do. Why do you think security is something that I might bring up from time to time?
The NSA.
The NSA. Okay, well, okay, think about the, have I ever displayed the live diagram of
Yeah,
the
the
United
IP
States getting
mining.
attacked?
Yeah.
Okay, so enough said, right? That was a hand earlier. Yeah, go ahead.
I was gonna say that, like, you might not always guarantee 100% security.
And by the time you have solid proof, like I can scan the system and find the virus, which is often